So we have to make an effort to finish classification today, so there's lots of things we need to discuss, but they're actually useful later on in the course as well. Let me get this thing out of the way. So if you remember, most of the models we discussed were generative, which means we started with conditional class probabilities, and we consider Gaussian, Bernoulli, and I also hinted that things can work for any distribution from the exponential family, but at the end of the day, we managed for two-class systems basically to put the posterior probabilities in terms of logistic sigmoids, okay? But I want you to remember those logistic sigmoids came after manipulating these conditional Gaussian distributions or whatever other distributions we used. So we did not start with logistic sigmoid. It just took that form. Similarly, for the multi-class problem, with the same assumptions for the conditional distributions, we came up that the posterior probabilities were written in terms of a softmax transformation, okay? E to the alpha k divided by the summation of this e to the alpha k's. So what we want to do today is somehow, rather than starting with some class condition distributions, go directly to a discriminative approach that gives us basically the posterior distributions, P of C k given x, directly in terms of some activation function, for example, a sigmoid. And we will see why there is benefits to do that, at least in the number of variables that we have to use to train the model. So before I do this, so in this, usually in discriminative models, it is very common to transform X to some future space. So let me just say a word. We already have discussed it, but let me just start with one picture to introduce what the idea is. So imagine you have this blue and red points, okay? And the actual classifier here, if you want to separate the two classes, is nonlinear. It's that black circle that you see in the middle. So we haven't really said anything about how to compute this nonlinear boundary, but I suppose if you use class conditional distributions with non-equal covariances, most probably you will get this, okay? But here is the idea. Imagine that you use transformations, you do some pre-processing of X, and you transform X through two Gaussian basis functions, and you see those two Gaussians here. Okay, these are the centers of the two Gaussians, all right? So we transform X to phi1 of X and phi2 of X. And what you see on the right-hand side is the data plotted now in this future space, phi1 of X and phi2 of X. And when you look at the picture on the right, immediately you realize that you can actually fit a linear classifier that separates the data, right? You cannot do this with a straight line here. I mean, you cannot put a line here or a line there, right? You cannot separate it. But if you transform the data through some Gaussian basis functions, then you can actually separate them exactly with this straight line. So you can think that this hyperplane basically is mapped to this black separating surface that you see on the left, okay? Now, you may ask, so can you give me any data, and can I find phi of X that somehow achieves miracles like this? The answer is no, all right? But in some sense, and we will talk about this, assuming there is any time left in the semester, there is a way to actually, rather than pre-assume what these functions are, adapt these functions to the data so you can achieve something like this. So we're going to come back to this topic again, assuming there is time. But with fixed basis functions, you can actually manage to be lucky and have a separation here with a linear hyperplane. But actually, you can also manage to take this data to a situation that there is so significant overlap that you will be way worse than you are already in the original X space. All right. So let me, with that said, right, let me go directly to this discriminative modeling and see what type of algebra we will need to do to train this type of models. So first, the definition. We don't have any class conditional distributions. We don't have any priors, none of the above. So what we do is we postulate that, so remember phi, I'm going to use phi now instead of x. The idea here is that we're allowed these models to map x to some future space. So think, in case you get confused, think of this phi being x, right? Okay, so what we do is we postulate that the posterior of sigma 1 given phi is given by some nonlinear function of a linear transform of phi, okay? And in this case, because we're talking about logistic regression, that activation function is a sigmoid. And I remind you what the definition of the sigmoid is. Remember, we came up with this equation, but we assume Gaussians for the class conditional distributions. We took the same covariance, we plugged in things, and then by a miracle, we got something that looks like this. Here, I don't do any of that. What I do is I say, I'm going to approximate this with a sigmoid function that operates on W transpose phi. No class conditionals, no Bayes rule, none of the above. Okay, and you may say, well, if the final equation is the same, what have I gained? Can you tell me what have you gained from the generative case? I mean, the final equations look to me identical, right? They're identical, so what's new? What have you gained? So remember, in the generative case, how many parameters we had in the model? Let's say we have two classes. What were the parameters in those two classes? So here is the count for the logistic regression model versus the generative version of this. So let's say that this is, we have an m-dimensional future space phi, all right, which can be the same dimension as the original space x. So we have, in this model, we have m parameters, all right? So take phi equal to x, and the dimensionality of x is m. So m parameters. In the generative model, you know what we have is, we have two m parameters for the means. We have two means in m dimensions, two m parameters. You remember they share a covariance, which is symmetric, so you have m times m plus 1 over 2. And then what do you have? You have two priors, so they are sum equal to 1, so plus 1 parameter. So you can see here the cost is m squared for a generative model versus m for a logistic regression model. So rather than training m squared parameters, now we only have to train m parameters, even though the model at the end of the day looks the same. All right? Now keep in mind, having a generative model has lots of other good things, right? You can talk about outliers, you can generate more data similar to the ones you started with. You don't have any of these things here. But if your objective is to actually only do classification, this model is way simpler, okay? Because it only has m parameters versus m squared that you get in a generative model. Also, here, unfortunately, you notice because this is a nonlinear function, somehow the very nice MLE estimates we did for generative models, unfortunately, will not be applicable here. So the calculation of the MLE estimates would be more involved, okay? And it's worth doing it because the same problems appear in many other settings. So let me first postulate what the likelihood will look like. So given the parameters W, all right, and given n data points, which you see here, So these are the inputs, and for each input I have the labels that they are either class 0 or class 1. Okay? Would you agree with me that the likelihood looks like this? Remember, t is equal to 0 or 1. So for each point, what is y, right, is this posterior probability of sigma 1 given phi n. Okay? So would you agree with me that, right, that the likelihood would be yn to tn, 1 minus 1, yn to 1 minus tn? So if tn equal to 1, you only get this. If tn equal to 0, this gets q1 and this gets q1 minus yn. Okay? So if you take logs of this, you get the very famous loss function, which is the cross-entropy error function. All right? That comes in millions of different settings in machine and deep learning. Okay? So, so the error function here is the cross-entropy. And again, t is coming from my training data, is 0 or 1, and y comes from my logistic regression model that gives me the posterior distributions. So yn, the definition is this for class 1, given the data point, if you like, phi n. So again, yn is the sigmoid of alpha n, and alpha n is w transpose phi n. Pay attention to all the notation because I'm going to start taking derivatives and things may get a little bit messy, okay? So phi n is the input, w transpose phi n, it's a linear combination of the input. I operate on this with a sigmoid and I get yn, and that's the cross-entropy function. A calculation that it's trivial, takes one line to solve, but it's going to be used in every slide in the lecture today, is if you take, so if you have the sigmoid as a function of a, and you take the derivative of the sigmoid, you get sigma times 1 minus sigma. So I want you to remember the derivative of a sigmoid with respect to its argument is sigma times 1 minus sigma. So if we try to minimize the cross-entropy and we take derivatives with respect to w, right? Because this is what we want to compute. This w is the unknown, okay? So what we will need to do is we're going to have to take derivatives of these logs with respect to y. So 1 over yn, 1 minus, 1 over yn times minus 1. And then we're going to have to take a derivative of y with respect to a, which is sigma times 1 minus sigma. And then derivative of a with respect to w, which is phi n. You see all of the above? The chain rule. So derivative with respect to y, derivative of y with respect to alpha, and derivative of alpha with respect to w. So you get phi n, and then times yn minus tn. A wonderful formula, which is the formula we have by miracle seen coming in everywhere. Is this familiar? You remember this is the error weighted basically by the input, the transform input point. Remember, where did we see this before? We saw it many times, but the most obvious place we saw it, where was it? For what type of problem? When we use the L2 error, the mean square error in the regression, what did we get when we tried to do an online MLE estimation? We got exactly the same equation. The only difference in that case, right, t was a scalar, it was the target value. Y was the regression model, which was actually in that case, it was W transpose the basis functions, okay, times phi. So we get exactly the same equation in the context of logistic regression, which tells you actually there must be something there that generates this nice form, all right? And if we have time, we will discuss this at the end of the lecture today by providing some generalization of these things. Okay, so how do we do stochastic optimization of this? Very simple, right? We use, how do we call this formula? gradient descent, but what was the original sort of algorithm in the 60s? Robbins-Monroe, okay? So we update this sequentially. This is the learning rate. We do it one data point at a time, and that's the very nice formula that gives you all the answers. So let's discuss some pathologies now in the context of logistic regression for this situation to see what exactly is happening. So I am going to take data that they are, we assume that they are linearly separable. So we know there is a solution, right? We can separate them with a linear hyperplane. So remember that the posterior probability is given by the sigmoid of W transpose phi. So obviously you can say based on the posterior probability, if the posterior probability is higher than 0.5, it's class 1. If it is less than 0.5, it's class 0, all right? And sigma equal to 0.5 for the sigmoid happens when the argument is equal to 0. So basically, any decision boundary that separates the data has to satisfy this condition. So when W transpose phi for a given point is greater or equal to 0, we call it class 1, otherwise it's class 2. Okay? All right, this is basically the decision we take by saying anything above 0.5 is class 1 and below is class 0. So that leads to W transpose phi equal to 0 and a decision that is looking like this formula that you see here. All right, that's one thing. Let's go back to the gradient, right? So if the problem is linearly separable, right, when we try to calculate W, we're going to find actually a W that minimizes the gradient. So minimizes the gradient means that Yn has to be equal to Tn. But Yn is the sigmoid of W transpose phi n. So I want you to think that how the sigmoid looks like, right? It looks like 0, and then, and then it flattens. So this says that for every point n, all right, Yn equal to Tn. So what happens to that sigmoid if you think that for every point n is going to give you Yn equal to Tn, and Tn, remember, is 0 or 1. So how does that sigmoid needs to look like to give you basically Yn equal to Tn, which can only be 0 or 1? Step function. Step function. It has to be a step function, which means basically for every training point phi n, W transpose phi has to go to plus minus infinity. Okay? Which means that the magnitude of W has to go to infinity. Okay? So let me, when I'm rewriting this equation, the slide says the same things, but when I say Yn equal to Tn, so basically either Yn equal to Tn equal to 0, so it's class 0, or Yn equal to Tn equal to class 1, but the bottom line is, if all of these things happening, every training point from each class k will be assigned a probability 1. So if something from class 1, we have probability 1. From class 0, we have probability 1. So it comes basically that there are multiple solutions here, all right? And we will see this visually. And every time you try to get, with this maximal likelihood estimation, with Robbins-Monroe, you try to get any of the solutions, the algorithm is extremely sensitive to where you start, right? So you're going to have to assume some W to start the iterations. So depending where you start, you get another solution, okay? And that's not very good, right? Because it's similar to doing least squares, let's say, but the metrics that you need to invert, it is basically ill-posed, so you cannot invert it. So we have a similar situation here. So let me give you a few lines on what is going on. So this is the training data. And you can see actually visually, you can actually put many different hyperplanes that separate the data. So it's not a unique solution. And what you see here are contours of the log likelihood. And remember, the log likelihood is this cross-entropy. And this line This blue line starts from the origin. This is 0.00, and it goes all the way to infinity, where it is the exact, the MLE estimate says basically when the gradient gets to 0, W goes to infinity. All right, so basically as we keep going from here to infinity, we are getting different solutions. And what you see here, the different colors for these lines correspond actually to different points on this line towards infinity. So this is 1, 2, 3, and 4. 1, again, I suppose this is 2, this is 3, and this is 4, okay? So what do you do about if you want to resolve this problem with the non-uniqueness of the decision boundary? Basically, you have to do regularization. By now, you know how to do this. And the easiest way is basically to do this in a fully Bayesian setting. So rather than having W as a point estimate, you put a prior on W, and you compute the posterior of W. And we're going to do all of this. And in that case, you know what? A plot like that makes an absolute sense. Because you can say, if I have a posterior of W, for each sample, I am going to get a different boundary. And those are what you see up there. Okay? So we will see this in a few minutes or so. All right. So we discussed about this Robbins-Monroe algorithm. So what we need to do is now we need to go a little bit further and do a little bit better by introducing this algorithm that is called Iterative Reweighted least squares method, okay, that is relevant to a huge class of problems in machine learning in the context of stochastic optimization. But basically, there is nothing new here. The method is nothing else but what's called a Newton-Raphson update, okay? So what I'm giving you on the equation at the bottom is an update of W, where H is the Hessian, is the second derivative of the loss function with respect to the parameters, and this is the gradient. Anybody remembers? And I gave you, by the way, I put some refresher slides on optimization in the notes that are not covered, like very few slides, including the derivation of this. But can somebody remember maybe from where this formula is coming from? What is the assumption that leads to this formula? You have to assume that the function locally looks like what? That's a quadratic function, okay? And then basically you minimize the quadratic function, and that's how you get this, okay? Again, you may want to look at these derivations, it's elementary 101 optimization, but I want you to just remember fundamentally the Newton method is W nu equal W alt minus inverse of the Hessian times the gradient. Obviously, these calculations are generally very expensive because you have to compute second derivatives. First derivatives are already a pain, but again, the mathematics are so easy in this type of problems with these nonlinear activation functions like sigmoids that these calculations of H can be done analytically. And so we need to do them because when you do them, you learn about this algorithm that is very powerful and applicable to many different problems. So let me, before I apply this algorithm to logistic regression, can you tell me if I apply this algorithm to linear regression problems, what will this algorithm give me? Remember, linear regression is minimization of the L2 error, the mean square error. So when you write the loss function for linear regression, the loss function is what type of a function? What function is it in W? I heard it. So in the mean square error, what function is it in terms of W? Quadratic. So if it's quadratic, this thing is supposed to do what? Because it assumes a quadratic thing and it approximates it to come up with this formula. So if it's quadratic, what you will do? In one step, it will give you the exact answer. Is that the case? Well, let's see. You remember for linear regression, right? We had the target values. The regression function is W transpose phi. This is the mean square error. So you remember, if you take derivatives with respect to W, you get a gradient looking like this. And in terms of this design metrics, I write it like that. We visited this before. So the Hessian will be another derivative with respect to W, so it will be phi transpose phi. So the update formula will be W old minus the Hessian inverse times the gradient, which is phi transpose phi W old minus phi transpose T. And so this and this will give you W old, they cancel. And then what do you get? You get the least squared solution, which is the exact MLE solution. All right? So the new Newton method, in one step, it allows you for linear regression problems to get the answer exactly. This is not going to happen now in the context of logistic regression because our problem is not quadratic in W, right? There is a nonlinearity there with a sigmoid function that is not going to allow us to be as simple as that. So let's see how complicated the algebra can get. If you study carefully at the slides, right, you will realize the algebra is extremely straightforward, and really there's no complication. And any issue that comes, it's very well known in machine learning. There are lots of tricks to address everything, so the problem is sort of very nice at the end of the day. So what you see again, the first equation is our cross-entropy. We saw this before, right? I remind you what y was the posterior probability given as a sigmoid of alpha, and alpha is W transpose phi. Okay? So if you take the gradients, we already did, right, a few slides ago. If you take the gradient, you get this. So if you write this in a matrix form using the design matrix phi, remember design matrix phi, you know, when you start the problem, that's the first thing you do. If you want to put it in a compact notation, and you put all the data y, all the model predictions y in a vector form, and all the target values in a vector form, you get phi transpose y minus t. And when you take one more derivative, all right? So if you take another derivative, you're going to have to take a derivative here of y with respect to alpha. And you remember what's the derivative of sigmoid we said? Sigma 1 minus sigma. And then the derivative of alpha with respect to w, another phi. That's how you get phi transpose y1 minus y. I mean, it's really nothing. It's just algebra. Okay? You know what? I should go and remove all the slides from the web because we have 3 projectors, wonderful projectors in front of you, but still your computer is better than my projectors. No good. All right, no good. Okay, so we can write this in a matrix form, phi transpose phi, all right? And then we can put all of this in a diagonal matrix R with the diagonal elements y1, 1 minus y1, etc., etc. Okay? Now, to be able to, for the Newton method basically to work right, we need to be able to convince ourselves that the Hessian is a positive definite matrix. Otherwise, we're going to be in trouble, all right? And so it comes out that these diagonal elements here, all right, they're all positive. Why is that? Why those things are positive? Because y is a probability. It's less than 1, right? So this is positive definite. Everything is positive definite. Okay. So this problem is a convex optimization in W. So it has a unique solution. So let's write the solution. All right. So we see the Newton updates. The W new is the W old minus the Hessian inverse times the gradient, which is phi transpose y minus t. And if you rewrite things, all right, what you do get is phi transpose r phi minus 1, phi transpose r z, where z we have defined it iteratively as this quantity here, this vector. So immediately when you look at this formula, all right, it looks like least squares, right? I mean, because you remember in least squares you have phi transpose phi inverse times phi transpose some vector. So here it looks like least squares, but there is an R there, and that's why it's a weighted least squares. All right, it's a weighted least squares. Okay, and this whole algorithm obviously needs to be solved iteratively because, so we are trying to compute W, right? Is there any W dependence? Why do we need iterations here? Look at this formula. Why do we need iterations? All right, here I see a W alt, right? But why do we need, why do we need iterations? R is a function of what? R is a function of Y, and Y is a function of A, and A is a function of W. All right, so the weights basically are functions of the solution, so you have to iterate. But if this algorithm is not a big deal, what you see here, literally, it's 5 steps basically, written nicely, and it goes with this name, Iterative Reweighted least squares. Extremely powerful. It appears in many estimation problems in machine learning. So that's something you need to know. I think in the next 2 slides there is some discussion about some physical intuition of the form that you get here and what actually Z means and what actually R may mean, but they're really not relevant in the big picture. Okay? So you can put actually a probabilistic interpretation on R, because actually, you know what is R? What is Y, 1 minus Y, for binary distributions? If Y is a probability, right, for a binary variable, what's Y, 1 minus Y? No, what does the Y, 1 minus Y means for a binary distribution? For the Bernoulli distribution, what is that? What is that? I heard it. The variance. All right, so you remember when maybe in other courses when you do weighted least squares, right? You weight this with the variance. Okay, so there is sort of some interpretation you can put in on what R is, but at the end of the day, it is what it is, and we need to live with it. And so the interpretation is here. There's another interpretation you can read, but really you don't need all these fine details. Okay. Question now. Somebody will say, that's fine. You managed to do this algebra for the sigmoid and for 2-class problems. But really, we don't care for 2-class problems. We care for 50 classes. If we have lots of data, we need to be able to operate this for many classes. And if you remember, we cannot use anymore the sigmoid function. We have to use this function. And how do we call this function? Softmax. Okay? So we have to operate on the softmax. And actually, I just realized just before I was coming, I was looking at this again. Don't take this, point by point. You remember when we did, when we operated on, when we used generative models, right? We started with this. We took this to be Gaussian, and we had some priors. And then we plugged them in, and then things cancel out, and we got a linear alpha, all right? Okay, so here, we don't actually have any of these functions, okay? So maybe I should go and remove it. What we have is alpha k equal wk transpose phi, okay? Just remember that, okay? So our model is basically, these are the posteriors for each class, where alpha k is wk transpose phi. A small parenthesis, because this is not accounted in the slides, but maybe when you program this, depending on the homework you got from Suvik, you may have to worry about this. You remember when you look at these probabilities, right, when you sum them up, they sum to 1. So these WKs, they are not all independent. So you cannot go and, let's say I have a problem with 3 classes, I'm going to assume 3 vectors W1, W2, W3. You will never be able to solve this problem. So you're going to have to fix the W's for one of the classes and only compute the W's for the other classes. Remember this, because it's not in the slides. All right. So, we will need to repeat the previous calculations. We need to find the gradient, and then we need to find the Hessian. So the gradient, if you take remember here there's not only one alpha, right? There's capital K, let's say alpha. Okay, actually capital K minus 1, but as I said in the slides, we use K classes. Okay, so we need to compute the gradient of this with respect to alpha j. So you know how to differentiate this thing here. You need to trust me, because there is nothing. If you take the derivatives of this with respect to alpha j, and alpha j can be any alpha j, can be equal to k or can be different from k, then you get this nice formula where this is a delta function, okay? Delta kj equal to 1 if k and j are the same. So we can calculate the gradients of y k's with respect to the alpha j's. So if we can do this, we can also we can use. We did this for the generative models. We can use one of k coding scheme. So we have our target values, right, for each data point is 1 for one class, 0 for all the other classes, right? So we have one of k coding. So the likelihood basically looks like what you see on the first equation. You agree? So IID data, and then I put this posteriors to the power t and k. And this is product of overall the classes. But remember, for each point n, only one of these t and k's is equal to 1, the rest is 0. So you will only get the posterior of the class that that data point belongs. Yes? All right, this is, a standard way for writing the whole thing in a compact form. So this posterior, our model, we write it as y and k to the power t and k. Okay? So the notation here again is what is y and k? And little n will remind you a data point n. All right? So it's basically yk, the activation function yk, compute that phi n. Okay? And t and k is zeros or ones. So if you take logs of that, you basically get the cross-entropy function exactly as before. The only difference basically is now that we have a summation over classes, right? You have a summation over classes, and there is an index little k there, all right? Because we used this one of k, capital K coding. So this is the cross-entropy for the multi-class problem. All right, so so this is again the same equation. So we need to calculate the gradient now with respect to the parameters wj. Okay? Remember, actually it's here, okay? Maybe it's not here. All right, so remember alpha j is, so for each class we have a different alpha j, okay? And each of that has a different wj, right? So each class has its own vector of parameters, okay? So what we will need to do is we will need to take gradients with respect to wj, all right? And wj would be the parameters for class j. So how do we differentiate this with respect to wj? You have to take derivatives of y with respect to what? Y is like that, so we will first take derivatives of y with respect to what? To alpha j, and I gave you the formula, and then take derivatives of alpha j with respect to what? To wj, all right? Which will give us a phi n. And again, by a miracle of nature, even though the problem is different, we get exactly the same formulation as before. All right? So you can see when you take derivatives with respect to Wj, this is the class J, you get basically this error that point M commits, right, for class J, times the basis function, if you like, or the input vector phi n for data point M. Identical as before, so when you do Robbins-Monroe, the formula is identical. The only difference from before is you update this for the vector of each class. Right? So you can do this for class 1. You can run all of this simultaneously, basically, right? And you plug in the corresponding gradients, but it's the same formula, basically. Okay. And so the question now is, can I actually push this further, and can I use this iterative reweighted least squares method or the Newton method for the multi-class problem? That will require that somehow we take the calculations further and we compute the Hessian. And the answer is simple algebra. Yes, you can. Right? So the first derivative with respect to Wj is given like that. So what you need to do is to find the Hessian, take another gradient, but with respect to Wk, where k can be j, but can be anything else as well. Another class, right? Because we need to form the whole matrix. So the Hessian, second derivative with respect to the w's, basically, we will have this, but then we will need the derivative of y with respect to alpha k, and then the derivative of alpha k with respect to wk, which will give you a phi transpose there. Okay? So, so when you finish, you actually get the Hessian analytically by this very nice formula. So I don't know if it's in the slides. It's not in the slides, so you can basically the formulas we have before for iterative reweighted least squares, you can actually apply the same type of formulas, and we're done. Okay. Let me see if there is. All right. So if you try to apply this to a problem with 3 classes, basically you're going to have this softmax function. You're going to calculate these posteriors, and how do you assign the different regions for each class? Basically, you look at the regions where this posterior is the biggest, and you say that's region 1. Here, this posterior is the biggest, this is region 2, and this is region 3. And the separating, how do I find? Can somebody tell me how do I find these lines? I mean, looking at the functional form, right? Why are these lines straight lines? Say it again. Something equal to 0? Well, remember, each posterior is written as exponential of alpha 1 divided by all the summation of the exponentials. The other one exponential of alpha 2 divided by all the summations. So what does it make one boundary between class 1 and 2? Alpha 1 equal? Alpha 1 equal to? So this is for region 1 will be exponential of alpha 1. For region 2 will be exponential of alpha 2. This line needs to have what? The same. All right, so they need to be the same. So what you need to do is alpha 1 equal to alpha 2, but alpha 1 is a linear function of x. Right? And it's W1 transpose x, and the other one is W2 transpose x. So that's why you get a straight line. Right? So you basically, by playing with these posterior probabilities, you can get these lines. All right. I mean, this point estimates are nice, right? But the question is, can we actually be Bayesian here? So let's see to which extent we can push these things to a Bayesian setting. So obviously in a Bayesian setting, there are no point parameters W. We're going to have to assume some prior. So I'm working now with a logistic regression problem, and maybe if it's not on the slides, you can generalize it to the multi-class case. All right, so for the logistic regression problem, we have two classes. We put a prior, and I remind you the likelihood is looks like this, right? The t's, you remember, take values 0 and 1, so this is a very simple one. So the posterior of W is the prior times the likelihood. So if you multiply them, the log likelihood, you get basically the cross-entropy, which is what we were discussing already, and we computed derivatives and all of this. And then you get this exponent from the prior of W from the Gaussian. So can you tell me a nice approximation just to make things easy going for this, the posterior? I mean, here we have the posterior, but sort of, you know, it's not a Gaussian, right? Does it look to you a Gaussian? This plus this a Gaussian? I mean, these are sigmoid functions. There's no way I can make this Gaussian. So what can we do here, all right? Hopefully it doesn't say it explicitly, it's there on the slides. What can I do to approximate this more complicated distribution? Laplace approximation, all right? So what you do is take derivatives with respect to W, set them to 0, find a map estimate, compute second derivatives, all right? And estimate basically the covariance, all right? And then basically you are ready to go. And by the way, the calculations are straightforward, right? Because we already have done. We already discussed about first derivatives and second derivatives for this. So the contributions of this to the map estimate and the Hessian, it's straightforward. And you know how to do this for Gaussian. I give you the analytical formulas basically for the covariance. And then what you get with the Laplace approximation, you get an approximation of this posterior that's a Gaussian, centered around the map estimate with covariance ascent given by this nice formula. Okay? So when I was showing you before different samples of the separating hyperplanes, right? Effectively, you can think in a Bayesian setting, you sample from W, and for each sample of W, you actually have a separating hyperplane defined by, you know, W transpose, right? W transpose times phi, okay? And that's what we will try to plot here. So let me go in all details on this plot. I mean, sometimes, you know, you can learn way, way more by looking at this plot, looking at the program, because if you understand this plot, then you understand what the method does. If you look at the equations, equations are equations, don't mean anything. So here it says 2-class data in 2D, all right? Let's start with that. So I see this blue data and this red data. This is a prior for W, which we take it a Gaussian, a very spread, you know, very high. The covariance there is 100 times I, so that's the log prior of the contours. This is the log likelihood for this problem, and I remind you, right, when we computed the log likelihood for this cross-entropy, basically the W's were going to infinity, okay? We're going to infinity, and let me see, what does it say? Where is that? This is KC, log likelihood for a logistic regression. The line shown is drawn from the origin, the direction of the melee, which is at infinity. The numbers correspond to the 4 points in W space corresponding to the lines in A. So these lines I showed you before, these points, these W's corresponding to 1, 2, 3, 4, they give you basically these regression lines that separates the data there. This is so basically the same plot that we have seen before. This is now the contours of the posterior, all right? These are the contours of the posterior. I am want to assume that that's the map estimate there, that big dot. And these nice ellipses are actually the ellipses pointing to a Gaussian. So this is nothing else but the Laplace approximation to the posterior. And you may say, really, you're pushing. This doesn't look like Gaussian by doing like this. The answer is yes, we understand. It doesn't, all right? But maybe the results are satisfactory, okay? Maybe the results, and when we do predictions with this model, I'm going to show you that the Laplace approximation is not as bad, okay? But you can question it because the contours of the posterior basically don't look anything close to the contours corresponding to a Gaussian. All right. I mean, you remember in in Bayesian setting, it's not sufficient to tell me that you got the posterior of the coefficients W, because as I told you in lecture 2, who cares about W? W sort of is an intermediate parameter, but is really, you're not Bayesian unless you do predictions. And predictions require integration in W. So what does prediction mean? If I train the model with some data T, all right, here I have to tell you, so you may want to remember this, right, or take notes. I don't show you the inputs corresponding to this training labels T, because the notation then will be awkward, since I want to make predictions for a new input phi, which is also a vector. So I don't know what to put there. Do you put another vector phi for the training data? So you don't really do. So what you do is you keep the labels T to remind you that you have training data, but this phi that you see there is for a test input. You want to know what's the probability of sigma 1. Everybody sees that? All right? So the training data is T, okay, and obviously come with the corresponding inputs not shown. This is a new training input, and I want to compute the probability of sigma 1. So the classical way we do predictions in Bayesian setting, this is this likelihood, if I knew W, times the posterior with W integrated out. Now, the obvious thing you can do if you like that formula, but you don't want to do the integration, you can say, you know what, I am going to use a plug-in approximation, so a point estimate for W, and we already have said many times that point estimate would be to use basically, instead of W, to use not the map estimate, but the posterior mean. Of course, in our case, this is a Gaussian, so it makes no difference. So if you want to make a prediction for a point estimate, this is your prediction. All right? You put basically the mean of the posterior of W, all right? And this is, effectively, you know what this is? This is your logistic regression problem, but instead of W, you use the map estimate from the posterior. Right? You remember this is the likelihood, which is a logistic regression model, all right? But instead of W, you're going to use the map estimate of W. The same as the expectation. All right. If you don't want to do this, and there is a code in the notes as well, what you can do is, since this is a Gaussian, how about if you do a Monte Carlo approximation of this, right? I mean, I notice everybody who does some sort of deep learning, etc. It's all Monte Carlo, and everybody throws 10 samples of this and 5 of that instead of 10,000 samples, and they hope for the best. But if you take S samples from this posterior, then you can approximate the predicted distribution as this mixture, if you like, of sigmoids. Right? Not bad. You can do this very easily. All right? And of course, the potentially better approximation, even than Monte Carlo with limited samples, will be to plug in here the actual approximation that we came about, which is the Laplace approximation, and somehow try to perform this integration analytically. So in the next 5 minutes, I'm going to try to highlight for you the proof where we plug in here the Laplace approximation, right, the Gaussian, this is a sigmoid, and then we can see how we can integrate W out. Okay, I want to be sure that there are two plots that I want to show you. Okay, this is good actually. All right, so so these are the data. All right, and each of these separating hyperplanes that you see here, it's a W that has been sampled from the posterior of W. All right, remember I have a posterior here. All right, so if I sample a W, I can come up with a decision boundary, and each of these lines that you see, it's a decision boundary for different samples from the posterior. Now, this plot that you see here is way more interesting because these are contours of the predictive distribution that has been approximated with Monte Carlo samples. All right? So you approximate this distribution with Monte Carlo samples from the posterior of W, and then you plot different contours. And you immediately see that those decision boundaries where you just take samples of W are straight lines, but the contours of the predictive distributions are not straight lines. Okay?
Are the samples all intersecting through zero because there's no bias term?
So you remember in all of these calculations, in principle, you have to remove the bias, right? So yeah, so to do them right, okay? So if you check, you hit it, you can verify this for us, okay? So, but the point again here is that these contours of the predictive distribution are not straight lines, all right? So if you think about, when you do predictions, really you're going to say when the posterior distribution is greater than 0.5, it's this class, less than that is another class, and that predictive distribution, as you can see from here, is not a straight line. All right, it's not a straight line. And again, the approximation here is just simply using Monte Carlo estimates of W. All right, we have not used the Laplace approximation. This is another example that I think we may have seen in an earlier lecture, and it has to do with fitting a sigmoid to SAT scores of students trying to make decisions basically using some training data. What's the probability of passing or failing the test depending on your SAT score? All right. So you can see again these dots that you see here are the low scores, training data. The students fail, the students that are passed, and you fit the sigmoid. But you notice the nice thing is when you fit the sigmoid, basically you compute for. So I think each of these points. Let me see what it says. The red dots is the mean of the posterior predictive. So everything that you see here, it's a posterior predictive distribution. So you say to me, for this score, what's the probability that I pass? And you see, this is, let's say, the mean value, and these are the error bars. Very nice, right? So the whole thing, it's a predictive distribution. So when you look at it, at any value of the SAT scores, you basically have some mean prediction, but also you have the affiliated 95% credible intervals. And the median is given as well. The red circles again is the mean of the posterior predictive distribution. Very nice example, right? I like it. And there is lots of different settings where these SAT scores are used in machine learning, so you may want to actually spend some time looking at this picture. There is really, calculation-wise, nothing else but effectively around this formula, and it all depends what you do with this. There's a point estimate, there is a Monte Carlo approximation, and now I am going to tell you the more difficult calculation that has to do with using a Laplace approximation. Okay? And this is a very powerful result, actually, using the Laplace approximation to do these integrals. And it comes sort of, if nothing else, it motivates you to think that if you ever get stuck with predictive distributions that look analytically intractable, you can actually resolve things with the Laplace approximation. So I'm only going to highlight, right, what is going on. You guys read the rest, okay? So again, what's the predictive distribution? The likelihood, if when you W times the posterior, and the posterior we approximated with our Laplace approximation. Okay, so remember here the sigmoid depends on W transpose phi, and I indicate W transpose phi as A, as we have done before. So you can think basically that this is sort of a projection of you know, of W in the phi space, if you like. So what I'm going to do is, can I write this formula here? I have to highlight this because you maybe you should understand this part. Is this formula correct? So we said, you know, I'm just writing the sigmoid, compute the W transpose phi. Can I write this formula? This is a delta function. It's okay? Right, by the definition of delta function? All right, so let's do the following thing. I have the sigmoid, you remember here I have the sigmoid times q of W dW. So remember here the sigmoid, I wrote it with this delta function and there's an integration in A, okay? So, so the sigmoid times q of W dW, I'm gonna have now, on the right hand side, I'm gonna have this integral in A times q of W dW. So I'm gonna have integration in W and A. So what I'm going to do is I'm going to switch the order of integrations, and I'm going to do the integration in A first. I'm sorry, W first, and then when I am done, I'm going to integrate in A. And it comes out that this predictive distribution that I need to compute, or the approximation, if you like, the predictive distribution, is given by an integral of the sigmoid calculated at A times some distribution P of A that is defined by this integral in W. I mean, I just call this to be P of A. And I want you to look now at that integral and try to guess how potentially, what type of distribution P of A is, and how do we compute it without seeing any slides. So P of A is an integral of Q of W, all right, where effectively, what do? Remember, W is projected on the vector phi, all right, and anything that is not projected in vector phi is integrated out. So what type of distribution, if you have a high dimensional distribution and you integrate many dimensions out, right, the new distribution, how do we call it? If you have something on x1 and x2 and you integrate x1, what is left is called what? Marginal. So really what this is, a marginal where all the dimensions that they are not projected in phi have been integrated out. And what type of distribution Q of W is? Gaussian. So if it's a Gaussian, can we actually just compute the mean and the variance and say that's it? How do we compute the mean and the variance? Well, the answer is very simple. So if we want to compute the mean of A, is P of A times A dA. And what is, so how do I get this? Help me here. P of A times A dA. All right? And remember, the P of A had an integration in W, all right? So there was a delta A minus W transpose phi, delta A minus transpose phi. So if I do the integration in A first, because there was a delta function A minus W transpose phi, what's going to happen to that A? It's going to become W transpose phi only. Correct? And then what do I have here? I have basically Q of W W dW, that gives me the mean of Q of W, which is the map estimate, times phi. All right? So effectively, you can do this for the mean, you can do this for the variance analytically, and you're done. All right? Basically, you have managed to approximate this distribution, all right, with a Gaussian, where you know exactly what the mean is and what the variance is. And of course, now the complication is, okay, we have managed this whole integral here, all right, this whole integral, to write it as an integral now of the sigmoid in A times some Gaussian in A with A, and then we have some integration in A there. So this is what we have to finish up the job. We have the sigmoid, all right, in A, P of A, dA. Remember, there's no W now. What happened to W? There's no W, right? The W's are where? The W is whatever we have, right? They're parts of the mean and the covariance we got for this distribution P of A. So what we need to do is, we need to calculate an integral of the sigmoid with a Gaussian. All right? And if you check on Wikipedia, integral of sigmoid with a Gaussian, they will immediately throw you a formula. All right? And if they don't throw you a formula directly in terms of the sigmoid, they will give you a formula where instead of the sigmoid, you actually have the CDF of the normal Gaussian distribution. But you remember in an early lecture I told you that the good approximation of the sigmoid is this CDF of the normal Gaussian evaluated at lambda times A, where lambda had a specific value to match the slopes at 0. And what was that value of lambda? It was square root of pi over 8. So, bottom line, you can use this analytical result. That is, there is a proof in the slides, because when I see a formula, I am as curious as you. I don't believe a thing unless I prove it, okay? Because if you don't prove it once in your life, and you use it the rest of your life and it's wrong, you are ruined. You have to prove it once, okay? So if you prove it once, and you have it, so you can look at it and admire it, the formula says that, okay? And there is the proof, all right? And here's the final answer. It comes out that the predictive distribution, so for a new input, if you say, what's the predictive distribution I'm going to be in class 1? It is defined by another sigmoid. Nice, it was anticipated, okay? Where this coefficient k of sigma squared is given like this. And in a particular case, okay, I call this k of sigma alpha squared. So this is the variance of that alpha distribution that looks like this, okay? This is the mean. Everything is defined, okay? So basically, if you want to do predictions, all right, you basically have to, you give an arbitrary input, so you evaluate the mean and the variance. So your mean is here, the variance defines what k is, you evaluate the sigmoid, and you're done. Okay, and it comes out, if you're only interested in sort of the misclassification error for this type of a problem, you didn't really have to do all the mathematics, because the separation boundary, it's still defined when this posterior predictive distribution is 0.5, and this is 0.5 when this is 0, and this is 0 when the mean is 0. So you really get sort of a point estimate. You would have easily plugged in, the map estimate for W and say my decision boundary is this, okay? But as I showed you before, the contours of the predictive distribution are not straight lines. So if you're interested on something sophisticated, you can go, you have to do this type of analysis that you heard today. So here again, the same samples. These are decision boundaries, if you like, where in the predictive distribution for a given input x, I use a point estimate for the parameters w, right? So here it's again a plug-in approximation, This is what you get, all right? These are samples, so these are the separation boundaries for different samples from the posterior of W that we approximated as a Gaussian. And the last two plots are basically the predictive distribution, the contours of the predictive distribution. And we said they are nonlinear. This is what you get with Monte Carlo, right? In principle, if you have lots of samples, this is the exact solution. And this is what you get with the Laplace approximation. It doesn't look as bad. I mean, considering that we approximated all of these sigmoids and all of these things, with a Gaussian, it doesn't look as bad, all right? So you can, again, this is sort of, you can consider, asymptotically as the number of samples increases, this to be the exact predictive distribution. This is the Laplace approximation. We only have 4 minutes, which is not very good. I almost wanted to finish today everything. So let me just show you. It will take us only 10 minutes on the lecture on Thursday. So to finish these things, we need to discuss a very similar model to logistic regression that is called a Probit regression model. So let me just define it in 4 minutes, and then we will continue this on Thursday. So here is, so we assume we have two classes, all right? And everything we have done up to now, right? We had the posterior distribution, and we defined some activation function that, let's say we took it to be a sigmoid of alpha, and alpha was W transpose phi. So let me define a new model that operates as follows. We're going to call something class 1 if an is greater or equal than some threshold theta, where that threshold theta is drawn from some probability distribution pi of theta. Okay? Otherwise, we're going to assign Tn equal to 0. So I repeat again. We have some noisy threshold that is coming from some distribution P of theta. And when alpha n, so for a given input, when W transpose phi is greater than or equal to theta, we assign class 1, otherwise class 0. Why is this interesting? Let's see what happens. Let's put this in a mathematical form. This model, the posterior of t of being t equal to 1 given my input phi, according to this definition there, is the same as the probability of theta becoming less or equal to alpha, which is W transpose phi. You see that? All right? So this becomes basically a CDF. Can you see this? This is the CDF of pi of theta. All right? So effectively, I have a CDF of theta. All right? And that CDF of theta is my activation function to define the posterior probabilities. So now you may say, you know what? The fact that that CDF that we discussed before as an approximation to the sigmoid doesn't surprise you, because now you see the CDF actually coming directly instead of using a sigmoid function. But actually, the two approximations are completely different and have completely different properties. This is not an approximation to the sigmoid or anything like that, right? So not only that, but we will see on the lecture on Thursday that the behavior of the two models in the context of outliers is very much different, okay? Because the sigmoid decays exponentially differently from the Gaussian that has this quadratic nature. So it's 1:44. I can finish early because the lecture was cut 6 minutes early last time, and that was not good. Okay, so we will see you on Thursday to finish and then start a new topic.